Now in section 9.1, when we had our formula for proportion or one proportion confidence interval, you can see it right here. It used Z alpha over 2. That was all well and good, and the reason it could use that is because basically this square root in the back, the square root of p hat times 1 minus p hat, is more or less assumed to be very similar to the sigma value, the standard error for the sample proportion. But the problem with that is that we had a z-curve, that's all well and good, but in section 9.2 we cannot use the z-curve. That's because we do not know sigma anymore. In the earlier section 9.1, we assumed this was basically sigma, and it's kind of a rough estimation, but it'll work, right, for our purposes. But that's not going to work anymore because we don't have that elaborate formula built off of the binomial distribution. That's where this comes from. So since we don't have the binomial distribution, we only have mu and x bar and stuff like that. We're stuck with using a different curve called the t curve, the student's t distribution. All right, so I've drawn it for you so you can see. So there's a z curve in here and a t curve. Let me label them for you. All right, so I labeled them for you. The black curve right here is the standard z curve you know and love. It's the standard normal curve. This gray curve, this charcoal gray curve, is the T curve. And you can see that T curves have a lower peak, right, than a Z curve, and they have kind of fatter tails. And that's because they have a larger standard deviation. They have a larger spread because you're not allowed to use sigma. The black curve has sigma, the population standard deviation, which is 1. But the T curves don't get to use that. All right, so let's look at this T curve, this gray curve here, and see what kind of properties it has. Well, the first thing is that unlike the Z curve, there's actually lots and lots of different T curves. There are different ones for every degree of freedom. And we'll have a formula right down here for what degrees of freedom is. Degrees of freedom is n minus 1. Right, so there's your formula for it right there. You're going to use it a lot, so you'll get very used to it, but you can throw it on your note sheet if you like. Now the T curves are symmetric, just like the Z curves were. But they're symmetric around the mean in the center, and the mean is still 0. So that part hasn't changed at all. So they're still symmetric around 0. That's your mu. Now, this is a probability distribution, so the area under the entire curve has got to be 1, just like any probability distribution. That's one of the things we learn in Chapter 5. And that means that the area to the right of 0 and the area to the left of 0 both have to be 0.5, just like on a normal curve, because it has to be half the curve. And just like on a z-curve, the x-axis is a horizontal asymptote. You can see that gray curve kind of surfing along the x-axis there, right? It doesn't hit it quite as fast. Of course, it never touches it, actually, but it gets really, really close, but it has a fatter tail than that z-curve does. I mean, other than that, it looks a lot like a z-curve. It looks like a z-curve with fat tails. So it's more spread out, that's key, than the z distribution, right? It has fatter tails and a lower peak. Let me write that out. So it has fatter tails and a lower peak in the center. That's what it means to be more spread out, right? More spread out than the z distribution. And then as the sample size increases, the density curve gets closer and closer to the z distribution. So as t gets, as the degrees of freedom gets larger, n gets larger, your sample size gets larger, then this little gray curve is going to get closer and closer and closer to that black curve. If you're taking calculus, it's a limit argument, right? The limit of the t curve is the z curve. And if you haven't taken calculus, then don't worry about it. No biggie. All right, so what I've done for you is I've drawn 2 t curves here. One has a degrees of freedom of 4, and one has a degrees of freedom of 1. Label each one. So remember that according to this bottom one right here, as your sample size increases, as your n gets larger, then your density curve gets closer and closer to a z distribution. So let's think about this. If your n is equal, if your degrees of freedom is equal to 4, that means that your n is equal to 5. Let me write that out. Okay, so if your degrees of freedom was 4, that would mean that n is 5, because the way you get your degrees of freedom is n take away 1. So 5 take away 1 makes 4. If your degrees of freedom is 1, that would mean that n is 2, right? because 2 take away 1 is 1. All right, so now remember that the larger your larger n has a t curve that is closer to the z curve. So when you look at these two graphs over here, the black one and the gray one, which one of them is closer to a z curve? Well, a z curve has high peaks in the middle and low tails on the bottom. Okay, so that must mean that the black one has a higher peak, so that's closer to a z curve. So that means that that's the one that's degrees of freedom 4, right? So df equals 4 is the black curve. And df equals 1 is the gray curve. All right. There, and I've labeled them for you right here in the graph. I don't know if it's easier to think of it as being kind of that part inside the tail right there. So that's the gray one. The gray one is the degrees of freedom is 1 and n is equal to 2. And the black one there is degrees of freedom 4, n is equal to 5. All right. Now I want to stop right there, even though I could go on. But the next part is finding the t-values, finding the critical t-values, just like we found critical z-values in section 9.1. So I want to pause, and we'll come back in the next video to do that because I want to make sure I have enough time to show you all the examples. So I'll see you back here then to find critical t-values.